right, two remaining problems. First one, to determine if the BJT transistor being operated in the linear, in the saturation, or in the cutoff region. Okay, if I give you a circuit VCC, which is 12 volts, RC, RB, run it. So the question is, determine whether the transistor is biased in cutoff, saturation, or linear. So where are these region? Sorry, REGION. IC, BCE. The BJT transistor IV curve. So that's cut off. Barely getting any collector current flows through the junction. And this is called, so which is saturation, which is linear? In BJT is kind of different. It's confusing people, okay? So you don't need to dig too deep in here. Let's just remember the name of it. So this is called the linear region or active region. And this is called saturation. And you want to operate the transistor in the linear region to get the largest gain. So case A, RB is 75K ohms. RC is 1K ohms. And now determine whether this is being operated in one of these three regions. It's very simple. Let's just go through the process, just 2 steps. The first step, to find out IC set. So you already have the load here, RC, or we can say it's RL, it's a load resistor. And you can definitely construct a load line. You're going to see this in the homework assignment a lot. Can you? You know the voltage here? Can you construct a load line of it? If these are given. How to construct a load line? Very simple, right? That's a load line. And that's VCE, that's IC. And you can also find the Q point. So now you just draw it, but also you have to label it. So what is this? What is this? What is this? It's not very difficult to calculate it. So IC set, the saturation current, collector current, calculated by setting VC to be 0, because you can look at the coordinate here. VC is definitely 0. We are trying to calculate IC on the y-axis, right? So you can label IC here, and then you assume IC to be 0 to calculate VCE, which is 12 volts. Okay, and then find the Q point. Here's 0.7 volts for the VBE, the PN junction built-in voltage, and then calculate for VB or IB by using this minus this divided by RB. So IB is calculated, and then you can find beta. Beta is usually given. Let me see what we are using here. 100. You can find IC, right? But no, we are not trying to find the load line. It's just trying to tell where this is being operated right now. What's the easiest way to do it? So first, you want to find the IC set, which is 12 volts minus 0, which is the VCE, over RC. Because when VCE is 0, you are getting IC set, which is 12 over 1K ohms, which is 12 milliamps. This is not the current where this transistor is being biased at. It's just the extreme case, right? So whenever VC is 0, the IC set is this value. And now let's look at IC, see if the IC is lower than this. If IC calculated IC is larger than 12 milliamps, it's impossible because this will be the largest IC you can get from this circuit. So what is IC now, or ICQ, right? The Q point is being biased right now. Maybe not Q point because it's not being biased in the active region. Let's just calculate for IC. It's 12 minus 0.7 over RB, so which is IB times beta, and that's IC. And what is that? It's calculated as 50 milliamps. It's even larger than IC set. Is that possible? Definitely it's not. Okay, so we assume it's being operated in the active region. That's why we can do this beta times IB equals to IC to the current, use the current gain. It only happens in the active region. And now we assume it's being operated in the active region, and we do the calculation, find out it's impossible. So we can find out actually it's not, it shouldn't be calculated in that way. So it's not being operated in the active region. Okay? So it's going to be in the saturation region. Is it possible that this guy is being operated in the cutoff region, so it's not on at all? You can look at the voltage here, 12 volts is way larger than 0.7, right? It's larger than the threshold voltage. It's going to open it up. So it's not cut off. And it's not active, so it's going to be saturation.
So in these examples, we weren't sure if the VC 0.7 or not, changed.
This one?
Yes.
Yeah, they are. So all the voltages are being used here are pretty large. It's way larger than the little change. And we are doing DC analysis. We assume it's going to be 0.7 volts. If it's not 0.7, it's going to be like 0.69, 0.61, 71, things like that. Yeah. Another case, let's find out the active case here. Okay, so when RB equals to same circuit. So calculate for IC set first. It's 12 volts minus 0 over 1 k ohms, which is 12 milliamps. And IC equals to beta times 12 minus 0.7 over 150K. So 7.5 milliamps, which is smaller than 12 milliamps. So it's in a linear region or in an active region. Okay, so that's it for these type of problems. You'll probably see in homework exams, quizzes. And we were talking about one example on Monday, I guess, but we didn't finish it. It's not an analog class, so we are not going to do the AC analysis of this type of circuit. But just one really quick example, so you know where this is being used in real world. Okay. RL is 1.2K, VCC is 12 volts, VRE is 1 volt, beta is 100. Okay, that's all the parameters that are given. So this is given because this is the load, right? It's the sum of the device we're going to plug into the circuit. And remember, that's a voltage divider. It provides a DC biasing voltage because this voltage divider is directly, it's a superposition, right? So the AC signal from the sensor has unpredictable DC offside. You know, it can be anywhere. So we want to remove it first using this cap. Bring it down, bring the AC signal down to the baseline, and then lift it up to the desired DC offside, the swing baseline. That's how you can do it by adding a voltage divider to it. So DC voltage divider, the VCC is being divided by the two resistors. Okay, so it's going to lift the AC signal up to the desired Q point. All right. So this resistor, and this resistor are not given, they're unknown. That's why it's asking you to design the circuit. So the cap is right, the cap is just the future. We don't need to design a cap here as well, right? But only the three resistors. What are these values should be? So from these parameters, we know that this voltage is being kept or is being held at 1 volt. You know, this is being added, RE is being added to the circuit. We just assume this is 1 volt. Okay, we are not changing it. So where can we get started? So there are several principles when you are designing this little BJT amplifier. This voltage is given, so you know the voltage level at this point. And you know the voltage here, so you can get IC. Over what? Or IC set. Can you get IC set? So that's the largest IC you can get from this circuit, right? When you assume VCE is 0, that's the only voltage drop at the bottom, and adding another voltage drop that forms the entire VCC. So VCC minus 1 over RL is a IC set. So that one is calculated as 9.2 milliamps. Okay. Remember when we designed the amplifier, we wanted the signal to be, want the signal to swing in the middle. So we get largest range on both sides. So this is IC set. So let's design the ICQ to be IC set over 2. What about that? Okay. Then ICQ equals to 4.6 milliamps. This is where we want to operate this amplifier. So that's a DC current is always flowing in here because it's being biased at that Q point. Okay, it's being biased over there. If there's an AC signal comes in, it's gonna swing it back and forth. Okay, the DC signal is already sitting there. That's how you design it. So can I find IB? What is IBQ? 1 over beta times ICQ, which is 0.046 milliamps or 46 microamps. Okay, that's IBQ. And because this voltage divider constantly flowing a current from top to bottom, right? It's a voltage divider, it flows current from top to bottom. And we do not want that IB to be comparable to the current flows to here. So which means, or we can say we want this current to be a lot larger than this current. So whenever the signal is swinging around, it's not changing the load from this voltage divider. Or it's not changing, because you can see here, I got a voltage divider, right? And want this DC voltage to be stable. How can I make it stable? So DC voltage here to be stable. There will be a load, right? Because this is the entire thing is a load. After this point, it's a load. If the resistance here is making the combination of these two resistors a lot smaller, then what's going to happen? Or let's say that you just want to make this current, this DC voltage, is resistant to the changes of the current change here. How can I make that happen? So for example, I have a voltage divider. I'm going to use this voltage to drive the following circuit. But the thing is, I don't know what's the resistance of the load. Okay, so whenever the resistance of the load changes, it's going to affect the voltage here. Is that correct? So how can we make this voltage stabler compared to the other case? If we write it down, it looks like this, right? R1, R2, and here's our load. Okay? Here's VL. We hope, ideally, we hope VL equals to what? V in times R2 over R1 plus R2, is that correct? Ideally. But the problem is it's not this case. So in real world, VL equals to V in times R2 in parallel with RL over R1 plus R2 in parallel with RL. Is that correct? Okay. You don't want an RL to affect the overall resistance that much. How can I do that? So how can we make the RL is not affecting the voltage here that much? You have low R2 that works. So low R2 can give you a what? I mean, what's a fundamental thing running behind the thing when you get the low R2? Why it's more resistant to the changes? Yeah. So if you have a low R2, it's a shortcut, right? You just want to, so the current just want to go through R2, but instead of going to RL. So RL is not dropping a significant amount of voltage from the point, but all the R2 does. So you want most of the current flows through R2, but only a little stream flows through RL. Then it's going to work for that purpose. So in this case, it's the same thing. When we are designing the circuit, no one tells you which resistance you want to use, but we can, assume the current here is 10 times of IB. What about that? 10 times. Is that a lot larger? Usually, whenever it's 10 times larger, we can consider it's way larger than something. So whenever this is 10 times larger, IB, and we know IB right now, so we are assuming IR2 to be 10 times IBQ. We don't know the R2 yet. We have to start from the current. So IR2 equals to 10 IB. So IB flows in here is 10 times smaller than the IB flows in here. Okay? So the current starts from the VCC, is that correct? That's the voltage source. It's going to pump current downwards, right? So when the current arrives here, it's going to split in two branches. And we just hope this branch got more current than the other one. So this is 10 times IB, this is 1 IB. Okay? Is that correct? So IR2 is this. According to what? KCL? Kirchhoff current law, what is that? The current flows into the node equals the current flows out from the node. So it's not losing, you're not losing current. So these are the two current streams flowing out from this node. Is there any current flowing in that direction? No. For DC, no. It's disconnect circuit. So these are the only two branches flowing DC current. And we know one is this, one is this. So we can find out IR1, which is IR2 plus IBQ. Add them together, these two together, which is 506 microamps. All right. Do we know VB? So what's the purpose here? Let's just come back. I are doing this calculation, but forgot the goal. What's the goal here? We're designing the amplifier. Okay. How to design an amplifier? The NPN BJT transistor already given, and you're not changing any of these ones. So the only things that can change are the biasing resistors, right? And load is given as well. You cannot change the load. And you don't know RE as well. Just what you know is you want to hold this voltage at 1 volt DC. So literally, if you find out R1, R2, RE, you're done. And now we have designed IR2 to be 10 times IB. And from there, we can find out all the current in these branches. So now, can we find out R1 and R2 right now? And how? We know all the current, but we don't know the resistance. You know the current, and you want to find the resistance, you need the voltage across it. across every resistor. So according to Ohm's law, you can calculate for the resistance. But do you know the voltage across R1 right now? Let's look at each one each time, okay? So we know the current for R1, which is 506. Okay. So do we know the voltage across this resistor? We know VCC, which is 12 volts on the top. But do we know VB? What is VB? Yeah? Is that 1.7? 1 volt here plus 0.7, you got 1.7. So now it's ready to calculate for IR1. So IR1 equals to VCC minus VB over, R1, sorry, over IR1, which is 12 volts minus VB, which is 1.7 volts, over IR1, which is 506 microamps. So R1 equals 20.45 kilo ohms. So there, you cannot find a 20.45 kilo ohms resistor in the drawer, but could just find out something similar, like 20 kilo, 21 kilo, things like that. So we got R1. So what about R2? R2 is simply just VB over IR2, right? VB is 1.7 volts. IR2 is 460 microamps. So R2 equals 1.2 kilo ohms over the RE. RE. You know IB, you know IC. You can find out IE, which is IB plus IC. And you know the voltage across it is 1 volt DC. So you can find out IE easily, which is 1 volt over IC plus IB, which is 1 volt over IB is 46 microamps. IC is 4.6 milliamps. It's 216 ohms. All right. Any questions on this? So BJTs are current controlled current source. Is that correct? Because VCE, IC. The reason we call it current source is because it's relatively, ideally, it's a flat line over here. It's constantly providing the same current. It's not changing. But in the real case, it's not. But we assume that it's a current source because it's providing a current, constant current, it's not changing. And these ones are IBs. No. Yeah, IBs. So for a circuit like this, the gain is a current gain. That's how it calculates for the output. And then it's been converted into voltage because the output current times the load, you're getting a voltage. And is controlled by this current. Okay, but for the CMOS transistors, it's different. So the ones you laid out every week, they are voltage controlled voltage source. Voltage controlled current source. And they also have a similar curve like that. And this is ID S. This is VDS. And these are different VGS. And why we call it a voltage control current source is because the current is calculated by this square law equation. So you can see that it's a voltage, not IB. So that's how I calculate the gain here, and this is how I calculate the gain here. And the results are always current, but the parameters controlling this current output for the CMOS is the voltage, is the gate voltage, gate source voltage. So here is the current, base current. Any questions? I want to introduce a few concepts. These can be interview questions. So first is called Latch-Up. We just covered BJTs, so now you can understand what is this, right? So Latch-Up, which is something you don't want that to happen for the CMOS transistor. And the reason this happens is because if you look at this cross-sectional view of the CMOS transistor, and that's the N plus diffusion, P plus, so this is the PMOS being implanted into the N well. That's the NMOS. And we're going to cover like this substrate contact and well contact later, so you understand why we have to have a P plus in the P well. But now just look at this structure. Because it's been doped with N plus material, it's just so what's the N plus material? Phosphorus, right? What's the P plus? Boron, normally. And the substrate is usually a P type substrate. And N well, it's something you can dope. So it doped that area with the N plus material, so it's called N well. So the N plus node is even more concentrated than the N well. So the N plus, they are same material, but just more highly concentrated. Just more molecules in there. We can see it's an N, so it's a P here, it's a PMOS. So P, N, P. So that forms a transistor. So it's another, it's like a NMOS, PMOS, but in BJT transistors that have NPN and PNP. So operate in a similar way. So PNP is going to flow current like that, and NPN flow current from top to bottom as well. You can see here, you got a P, I got an N well, I got a P sub. So that's a PNP transistor. That's why this picture shows that transistor here. And then you have an NMOS on the other side. There are PMOS and NMOS everywhere on the chip. If there's an NMOS, like an inverter, right? You have a PMOS and NMOS pretty close to each other. So if there's an NMOS, then it has an N, starting with the N, and then P substrate, and then N plus. So it's like NPN. So the thing is, the current is gonna flow like that to the ground. It's like shorting VDD to ground because you are shorting this pin. Like this is like the top rail of the inverter, this is the bottom rail of the inverter, is shorting the VDD to the ground, which is very bad. You don't want that to happen to your transistors. And there's a way to avoid that in the fabrication, to make it a little better. There will be some current being lost, but the way you can avoid that or reduce the loss of the current is by implanting these trenches. It's called shallow trench isolation technology. It's actually being used everywhere for the any transistor being fabricated using anything anywhere lower than 250 nanometer 250 nanometer for the length, minimum length, and they have to use this shallow trench isolation. So this is the one transistor, and that's another transistor, and it has silicon dioxide or some oxide material has a high resistance in the middle, which can increase the resistance between these two transistors. So whenever it has an NPN, like PNP and NPN, it's trying to get a circuit and short it to the ground, it has this high resistance material in the middle to increase the resistance so it's not shorted to the ground. It's still connected to the ground, but not shorted to the ground. Okay. And you have a pretty large resistor here. Actually, it limits the current a lot. So the current flows from the VDD to the ground is significantly limited in that case. Okay. Something you want to know? What is a Latch-Up? In the interview, if they ask you, okay, what's Latch-Up? And what is pinch off? That's not a bad thing. It happens at every moment for the transistor. So for example, this is the NMOS transistor. Gate, that's a gate oxide, N plus, N plus. If you connect this gate to a voltage source, what's going to happen? Yeah, it's going to bias the transistor by attracting what to the channel? Yes, because this is a positive potential, right? So the electrons so whenever you turn it on, the electrons in the P substrate, this is the substrate, the silicon substrate, all the electrons were everywhere. But whenever you have a positive potential over here, so the electrons are going to move to the channel, to this area, and form a channel. Do you have any current flows in the channel yet? No. So that's why you need to turn on here as well to give a pressure to pump the current from D to S, or to attract electrons from S to D. Is that correct? So that's why this is source, this is drain, because it's naming these two nodes in terms of the electron, the direction of the electrons, because the electrons are being attracted here. That's why it's the source of the electrons, and the drain of the electrons as well, right? That's why it's drain and source. And when we are looking at the current, it's actually pumping the current in that direction, but physically electrons are flowing in that direction. Okay, and whenever you increase VDS at some point, it's going to look like this. The channel will change the shape. I mean, in a physical device, I don't think you are going to be able to find a line there, right? It's just showing you that because this voltage is relatively high, it's a battery, it's a pretty strong voltage source, so it's going to deplete all the electrons nearby. So it's going to deplete all the electrons here to make the electrons here less compared to this area. So at this point, we call it a pinch off of the channel. So that's a pinch off moment of the channel. And if you increase VDS further, what's going to happen is it looks like even more different. So what's happening in this case? Oh, say it again? Yeah. So do you still have electrons flowing in the channel? From the curve, according to your conclusion, it's going to be like this. But why it's not? I mean, physics is physics, right? It's different from like you are driving a car. You think there's no way to drive it, you should stop. There's no car anymore, but physics is not. Yeah, voltage is still here. I mean, it gets considered as a pretty strong voltage. And that's if you compare the size of the voltage source on the bench and compare the little tiny 180 nanometer transistor in the little silicon die, it's negligible. So that's why electrons will tunnel through the depletion layer and accelerate. It's actually even moving faster. Why it's moving faster? Because it has a, I don't even trust that. It sounds like mysterious, It accelerates what about that? So if you look at the electrons over here, it's very close to the voltage source, and if you have an electric field, that's an electric field, okay? And if you place the electron here, it doesn't have that long distance to travel, and the electric field will provide a force to the electron. So if you have a longer distance to allow the electron to travel, it's going to accelerate for a longer time, so the speed is actually higher. Higher. If you have a longer distance to accelerate, the electron will end up with a higher speed. This is what's happening here. So electrons are all accumulated on the other side, and because this is pretty strong, so whenever they are able to penetrate that layer, it's going to keep flowing in that direction, and there's no electron here anymore, right? Because they are all here. That's why they get more momentum when it reaches the other end. So you do still have current, but the thing is, it's not. It becomes flat because it's saturated. You don't have a larger channel, but also because they accelerate, so it has a higher speed. That's why it's actually going up a little bit. So it's not pure flat. Yeah, so it's called VDS set, saturation VDS. which is the name of it. It's called VDS set. That voltage equals to VGS minus VTH, N for the N transistor. So these are different VGS. Oh, straight. And now let's look at the different VGS. Does that make sense? I mean, it's going to saturate at some point. But if you bias the gate at a different level, it ends up with a different plateau for the saturation current. Why? So what is this called? Inversion layer. So we invert it by the voltage. So larger VGS, the channel becomes wider to get more charges. So larger current makes sense, right? That's why different VGS has a different width of the channel, or depth, actually. So the entire process over here, okay? So I don't want to directly just write down the definition. So I just described all the process for what's happening for the transistor by different VGS, different VDS, right? So the entire description here, including the pinch off, is just one moment for that process. And this is called channel length modulation. Or CLM. If during interviews they ask you, please explain channel length modulation for the CMOS transistor or NMOS transistor. Okay, so know how to explain that. Just make it brief. Summarize it. Like, what is CLM? What is that? When you keep increasing VDS, the channel length becomes shorter. Is that correct? Because that's a channel. What is a channel? Channel is an electron channel. This is not an electron channel anymore, but this is. It's more significant for smaller transistors. Or smaller technologies. Why? You can imagine if so, what's the smallest technology on the market right now? It's changing every year, not every year, every 2 to 3 years. So what's the smallest one now from TSMC, for example? 5, yeah, has been commercialized. It's right in your phone. If you buy iPhone 13 or something, like it's already in there. So what's going to happen for next 2 to 3 years? 2. Okay. So if you compare 500 nanometer technology and 2 nanometer technology, if you draw the 2 different transistors on the paper in scale, it's going to be like, that's a Apple III transistor, the CPU in there, the length of that transistor, and this is probably the 500 nanometer transistor you are laying out in the lab for the channel length. I'm talking about the length. Okay? So if that's the channel, and start doing that CLM thing. What's CLM? Channelless modulation. Start pinching off. Here. Just modulate. I mean, I don't care because I have 500 nanometers for to modulate. Modulate to here. It's not changing that significantly, right? But for the 2 nanometer technology, like whenever it changes a little bit, boom, change the lens like 50%. It's more significant to the smaller technologies. All right. See if there's anything else I want to let you guys know. Body effect. Those are the little things. So what is body effect? So that's a P-sub. That's the NMOS transistor. It's directly being fabricated in the P-sub, so there's no well. So you got a P, you got an N, boom. What's that? Diode. You are not intentionally to make the diode, but there's a diode. If you give a accidentally the voltage at the anode is larger than the cathode, then it's gonna flow current in here, which is bad. So what you want to do is, that's why in your layout, remember you have a top rail. The top rail is not just a metal wire. It's actually a P contact. It's a P plus, it's a P material. So P plus for the NMOS, N plus for the PMOS, for the well contact. This is called well contact. But do you have a well here? You don't. P well is the same as a P sub because the NMOS is directly fabricated in the P sub. The reason you need a P plus is P plus and P not really very plus, which is the P sub, right? So it's lower concentration of the P material, and they have the same material, so they are actually being shorted to each other. So for the NMOS, you always connect the body, so that's the body, or bulk, to the ground, because this P plus is shorted to the P sub, and the P sub is literally the anode of this parasitic diode. So which means you do not want the voltage here to be higher than here at any moment, because it's gonna, if this accidentally becomes higher, then current will flow into here and into the channel. Then what's gonna happen? So this voltage played so hard to invert that channel with electrons, and now it's injecting current to neutralize the electrons. So the consequence is it becomes more difficult to turn it on. Or you can say VTH N will increase. It takes higher voltage to turn it on. Okay, keep in mind, in interview, if they ask you, what's the consequence of the body effect? I'm going to ask you this for many times in the semester. It's a very common interview question. So what's the consequence of the body effect? Yeah, it's increase of threshold voltage of the NMOS or PMOS. Get it? And that's why. All right, we'll see you on Friday.